Part 1. A World of Opportunity. It was once thought that the only thing that was really important for pouring walls and columns safely was the engineering science of liquid heads and concrete forming equipment. Experience indicates a majority of form failures are not the failures caused by overloading a forming system. This presentation of concrete placement safety is an effort to improve job site safety and eliminate costs due to the root causes of most form failures, which are lack of knowledge, lack of experience, lack of supervision, lack of management. Let's put a positive spin on this and talk about producing successful projects by broadening our knowledge, expanding our experiences, improving our results, and becoming better job site supervision and management. Architects, engineers, and owners are demanding better quality concrete and finishes, and one way of accomplishing this is with the use of concrete additives. One of the long-established concrete additives is air entrainment, which is very important to make concrete more resistant to salt and the freeze and thaw cycle. The features and benefits of concrete additives are extensive. With a modest extra cost per cubic yard, the benefits to the project owner may be well worth the added cost. These benefits of using concrete additives include a superior concrete finish without the regular bug holes normally caused by water and air bubbles, increased flow of the ready mix with minimal vibration required for faster compaction with less labor, a lower water-to-cement ratio delivering higher strength concrete, easier to consolidate concrete around rebar, blockouts, and other openings, produces a finished architectural concrete product without rubbing and patching when formed with a steel form face sheet. When everything is considered, the end product will be much better and may come with a lower in-place total cost. A good ready-mix supplier should have the technical knowledge and experience to identify which additive or additives to use, how much to use, and when to add. The forming system you choose is also very important. With a more fluid ready-mix concrete, a stronger, higher pressure-resistant form system may be required. This is where good engineering and professional project management must fulfill their roles. At the same time, an experienced formwork supplier can help you to select the right system with engineering and field service. Concrete additives are changing the game, along with the advancements in concrete placement delivery equipment, adding a whole new dimension to the management requirements to construct concrete walls and columns. Failure of the formwork with a blowout during construction poses obvious safety concerns. These include possible loss of life and property damage, as well as financial burdens associated with the cost of cleanup, added time to an already tight schedule, labor, and replacement concrete. To avoid injuries and losses as a result of form failure, the talent and experience of all persons responsible for the project are required. To deliver a safe project, cooperation and coordination connecting project engineers, form suppliers, and project management is required. This video has been produced to help construction professionals, site management, site engineers, and site crews place concrete safely. Let's begin. Part 2. Formwork and Project Safety. Construction professionals that use concrete forming systems have learned the tricks of the trade that increase safety and productivity. This includes formwork system selection, assembly, erecting the forms, placing ties, bracing, plumbing, aligning, pouring, vibrating, curing, stripping, cleaning, and oiling the forms. There is so much that needs to be known and remembered about forming concrete that it is easy to overlook one of the basic facts. Concrete forming systems resist a lot of pressure. When not taken seriously, the pressure inside a form can get the crew into a lot of trouble fast. The pressure rating assigned to the form should never be exceeded. Safety on the job site is everyone's job. Get the facts, look for potential form failure situations, and take vital steps to make sure the crew makes it home to their families each night. Under the supervision of project management, it is the responsibility of the crew at the job site to construct and erect the formwork in strict accordance with the formwork design and layout drawings. Our long-term practical experience has led us to believe that most form failures are a result of form erection and assembly errors, primarily missing ties, clamps, pins, and braces. Form tie assemblies or parts of assemblies that are missing can quickly overload surrounding ties, contributing to a possible form failure. A safety check and inspection of the formwork during assembly and prior to pouring are required to ensure the safety and reliability of the formwork. Other contributors to formwork failure can be linked to retarding admixtures, as well as rapid placement systems, like pumps, conveyors, and cranes. Uncontrolled concrete placement and inadequate monitoring of concrete behavior before and during placement can have serious effects on safety and structural capacity of the formwork. A statement of potential problems related to the successful placement of concrete begins with the contractor and engineer's plan for the project. Project engineers, working with a competent ready-mix supplier, are required to select a concrete mix that will meet the structural designer's specifications. Next, project management will select a forming system that will deliver strength, flexibility, and the lowest in-place concrete costs while maximizing safety. They will develop a placement plan that includes criteria for concrete delivery and monitoring during the pour. It is also critical to monitor the concrete when using a vibrator. If the vibrator goes too deep into the pour, the concrete may liquefy and increase the pressure on the formwork to the point of failure. A strong indicator of pouring concrete too fast with a minor form failure may be a pillowed finish or small bulges in the finished concrete. Other failures may be the result of concrete mix errors exacerbated by the rate of pour, while a small percentage is due to form design errors. The brutal facts are that form failures can range from a pillowed finish to a total form blowout, which can cause severe injury or even death. Before discussing pour pressure design in Part 3, it is important to remember that all formwork is designed to a maximum allowable pressure rating. This rating cannot be achieved if the forms are not assembled correctly. For example, if one tie or bolt is not installed or is installed incorrectly, a form that is designed to resist 1,200 pounds per square foot of pressure may only be able to resist 600 pounds per square foot or less. Although formwork is designed to withstand concrete pour pressures from 600 to 2,400 pounds per square foot, the examples used in this video are based on formwork designed at 1,200 pounds per square foot. It is also important to inspect that every nut and washer on every tie is snug against the form. Even if a tie is installed, it cannot resist load unless the nut and washer are snug to the form. When they are not snug, the entire load is transferred to the surrounding ties, causing them to become overloaded and potentially fail. Also check that bulkheads and all other form components are properly installed and secured. In the end, a successful project can be defined by the following. Number 1. Zero accidents, injury, or property damage. Number 2. Correctly assembled formwork. Number 3. Ready-mix concrete placed at a maximum rate allowable in strict accordance with form design details. Number 4. Superior concrete finishes as a result of proper concrete design and formwork choice. And number 5. Lowest in-place concrete cost consistent with quality and safety requirements for the project. Remember, someone's life might depend on your work. In fact, it might be your own.
Part 3. Follow calculated pour rates. Now let's talk about the load that formwork must resist. pressure from liquid concrete. What is pressure? There is pressure in your car's tires, in the water pipes in your home, and in your arteries. All of these are examples of pressure. The concept of pressure can be very confusing, so we will explain concrete pressure using two containers of water. Let's first look at a short container and a tall container, both 12 inches in diameter. If we fill both containers with water and then drill a hole in the bottom of each container, which stream of water will shoot out farther? The stream from the taller container will shoot out farther because the water pressure at the bottom of the container is higher than it is at the bottom of the short container. This is because the water pressure is dependent on the height of the liquid. Height is the most important fact to understanding fluid pressure. Do you remember going to the pool as a kid and diving to the bottom of the deep end looking for quarters? The deeper you dove, the more your ears would hurt. This was because the pressure increased on your ears from the water above you. The pool didn't get wider at the bottom, you just increased the height of water above you. This example shows how pressure is dependent on the height of liquid, not the width. Now, let's look again at two containers both the same height, but with two different diameters, 6 inches and 12 inches. If we fill them both with water and then drill a hole in the bottom, the stream of water coming out of both containers is the same distance. Why? Because the pressure is identical at the bottom of each container. Again, because the pressure is dependent on the height of liquid. This means intensity of water pressure is not dependent on how wide the water is, only how deep the water is. So how does this translate to construction and concrete formwork? When poured into a form, liquid concrete acts identically to water in a bucket. The deeper the liquid concrete in a wall, the higher the pressure, and it's too late to add ties and yokes. There's often the misconception that the wider the wall, the higher the concrete pressure. But the truth is the pressure that concrete exerts on the form is entirely dependent on the height of liquid concrete. Because concrete contains sand and gravel, cement and water, it is denser and heavier than water. In fact, it is almost 2.5 times as heavy. Therefore, the amount of pressure that liquid concrete exerts on the formwork is 2.5 times higher than if you were to place water in the formwork. Now that we have covered how pressure is dependent on height of liquid concrete, let's discuss how this impacts concrete placement safety. Let's define the terms: liquid head pressure, allowable pour pressure, and pour rate. First off, liquid head pressure is defined as height of liquid concrete times the density of concrete. The result is typically expressed in terms of pounds per square foot. The liquid head pressure at the top of the wet concrete is 0, and the pressure at the bottom of the wet concrete is maximum. Formwork is designed and rated for an allowable height of wet concrete. The height of wet concrete multiplied by the density of concrete determines the maximum allowable pour pressure. The density of concrete is approximately 150 pounds per cubic foot. For example, when a form is rated for a pour pressure of 1,200 pounds per square foot, the form has been designed for 8 foot of liquid concrete multiplied by 150 pounds per cubic foot. These high pressures require the formwork to resist incredible loads. The result of ignoring them is form failure, and when a form fails because of incredible loads, incredible consequences occur. This is why it is so important to understand pour pressures and pour rates. So what happens if the wall is taller than the allowable height of liquid concrete? Well, fortunately, concrete hardens. Once it hardens inside the form and becomes a solid, it no longer exerts pressure on the formwork from additional liquid concrete placed above it because a solid object cannot exert lateral pressure. An example would be placing a large block of hardened concrete inside a form. The form provides no resistance to the block because the block supports itself and exerts no pressure on the form. Although hardened concrete at the bottom of the form no longer exerts additional pressure, bolts, ties, and other accessories cannot be removed until all the concrete in the form has hardened. If we know how quickly the concrete hardens, we can place the concrete into the form at a specific rate so we do not exceed the allowable liquid head. This specific rate of placement is called the pour rate and is given in terms of feet per hour. This pour rate is determined from the formulas found in the American Concrete Institute, ACI 347, Guide to Concrete Formwork, and is dependent on the temperature and chemical composition of the concrete. We encourage project management to review this material as there are special applications not covered in this video that can change the calculation significantly. Pumping concrete from the bottom of the form upward and using self-consolidating concrete are a couple of examples of applications that require additional analysis to determine the pour rate. The Serial Report 108 and DIN Standard 18218 are other good sources of information for calculating the concrete pressure on formwork. Let's look at why concrete temperature is important. A hot mix of concrete hardens faster than a cold mix of concrete, so colder concrete will require a slower pour rate. Why are chemicals important? Concrete with chemicals and additives like plasticizers tend to harden slower than concrete without additives. These mixes will require a slower rate of pour. The charts shown in a qualified form supplier's erection drawing should be used to determine the pour rate. These charts have been produced using the equations and information found in ACI 347 Guide to Concrete Formwork referred to earlier. If you use these charts correctly, the pour rate ensures that the height of wet concrete will not exceed the allowable liquid head. Now, let's take a look at an example that incorporates everything we've discussed so far. We have a 12-foot tall wall. The thickness of the wall is only important to determine how much concrete to order and does not affect the pressure in the form. The engineer has designed the forms to withstand 1,200 pounds per square foot of pour pressure. This translates into an allowable liquid head of 8 feet. The project foreman has determined the temperature of the concrete and taken into consideration the additives in the concrete from the batch ticket received from the concrete truck driver. The project foreman then uses the chart provided in the erection drawings and determines the pour rate to be 8 feet per hour. The crew starts to fill the wall up at 8 feet per hour. After 1 hour, there is 8 feet of wet concrete in the wall. Now, as they continue to pour concrete into the form, the concrete at the bottom of the wall should begin to harden and no longer exert additional pressure on the forms. If the rate the concrete hardens matches the rate concrete is placed into the forms, then the allowable pour pressure is not exceeded. Now, let's discuss how to use the pour pressure charts in the erection drawings. Engineers have determined the allowable pour pressure of the formwork. All you need to do is determine the additives in the concrete and its temperature. The components in the concrete mix that determine the chemistry coefficient are additives like retarders, plasticizers, and cement substitutes like fly ash, slag, and natural pozzolans. There are 3 places to find what components are in the concrete: the approved concrete mix design, the concrete order ticket, and the batch ticket from the concrete truck driver. While the concrete mix design provides the chemistry for planning purposes weeks in advance of a pour, it is best to use the batch plant ticket from the driver to check what components are in the concrete. This prevents accidents when the mix design has been changed and the crew has not been informed. Once you have determined the concrete additives, use the chart to determine the chemistry coefficient. The chemistry will determine what line you use on the graph. Next, find the temperature of the concrete by placing a thermometer at least 3 inches into the concrete per ASTM C1064 standards. Be careful that you do not use the air temperature. Concrete temperatures can be 20 to 30 degrees cooler than air temperatures, which can potentially double the pour rate in some cases. Now, find the concrete temperature along the bottom of the chart, go up to the correct chemistry coefficient line, and then over to the allowable pour rate. It is truly that easy. Let's do a quick example. The batch ticket shows that the concrete has retarders and fly ash. You go to your chart and find the chemistry coefficient is 1.4. You've taken the temperature of the concrete and found it to be 70 degrees Fahrenheit. Now you go to the chart and find the allowable pour rate is 5.5 feet per hour. This pour rate will also tell you how long it should take to pour the entire wall. Simply divide the height of the wall by the pour rate. 12 feet divided by 5.5 feet per hour equals a little over 2 hours. This information can be used by project management for planning purposes and to monitor and verify that correct pour rates are being used. If the wall in our example was finished in 1.5 hours instead of 2.5, project management knows that pour rates were not followed. In our examples, we have seen that changes in concrete temperature, concrete chemistry, and placement rate can increase the pour pressure in the form. Let's talk about how using incorrect temperature, chemistry, and pour rate can have serious effects on the forms. Number 1. A sudden change in concrete temperature may happen after a cold front passes through or with a change in the seasons. Aggregate piles can cool overnight, resulting in concrete being 20 to 30 degrees cooler than air temperatures. Using air temperature instead of concrete temperature can give a pour rate double the allowable rate. Number 2. Concrete chemistry can change. A project supervisor may change the mix design by adding a plasticizer or retarder to make the concrete easier to place in a form. This may cause the pour pressure to increase in the form. And number 3. Many contractors have started a pour late in the day, causing the crew to work late. It is tempting to increase the pour rate to finish early. Increasing the pour rate will increase the pressure in the form. Temperature, chemistry, and pour rate changes can increase the pressure in the form above rated pressure until some design limit is reached. Formwork is designed with safety factors which are required by industry standards and specifications. A contractor must never infringe upon the design safety factor by failing to comply with the drawings, exceeding the rated pour pressure of the formwork, or for any other reason. If pour rates are not followed, a tie may break, causing the form to bulge. The form may rupture, causing concrete to flow out of the form. In extreme cases, the ruptured form may become unstable and fall over. Many failures are simply an expensive mess to clean up. Some failures may cause injuries to workers. In the most extreme failures, workers may be killed as the forms rupture and fall over. This is why we need to learn how to control and monitor concrete pressure inside the form.
Part 4. Controlling the placement of concrete and monitoring its behavior. One of the most important steps in concrete construction is planning and controlling the placement of the concrete and monitoring its behavior during the pour. Before you get started, it's a good idea to create a pre-placement checklist to ensure the formwork has been constructed according to the formwork erection drawings. This includes checking that every tie, form connectors, bulkheads, pipe braces, scaffold brackets, handrails, and other accessories are properly installed. Keep in mind, the form assembly crew and the pour crew may not be the same workers. After the forms are assembled and erected, the form crew may move on to other tasks, leaving the pour crew to place the concrete. This fact alone is validation that a complete inspection of the form assembly by a qualified person is an absolute requirement. Have a pre-pour meeting with the crew so everyone knows what to expect. Review the planned rate of pour in feet per hour from the pour pressure chart. Use this to set an expectation for how long the pour should take if everything goes according to plan. When scheduling the concrete delivery from the batching plant, plan for trucks to arrive at intervals that correspond approximately to the planned rate of pour. For example, if a pour rate of 6 feet per hour corresponds to 18 cubic yards placed into the form, then schedule the 9 cubic yard trucks to arrive at 30-minute intervals during the pour. Once the pour begins, have a competent person record the arrival of each truck and communicate to the batch plant if the rate of delivery needs to change. This person can also monitor batch tickets to make sure that a different concrete mix is not inadvertently incorporated into the pour. Experienced contractors know that there are many factors that can alter the expected behavior of concrete. Understanding the behavior of your concrete mix before and after it enters the formwork can eliminate a serious accident. The following are examples of different methods used by experienced contractors to help them understand the behavior of concrete at the time of delivery and throughout the concrete placement process. Some of these methods are subjective and should not be relied upon solely, but in each case, effort must be made to determine if the concrete is setting up in the form according to expectations. Number 1. At the beginning of a pour, shovel a pile of concrete onto the ground in an area that will not absorb water. Cover the pile with a plastic sheet to reduce the effect of the concrete drying out. Check how the concrete is setting up by periodically stepping on the pile to detect firmness. If the concrete shows no signs of setting up after a half hour, there may be a problem. Number 2. Another widely used indicator of how concrete is setting up is to lower a long number 5 rebar into the wet concrete and allow it to sink until it will not move any deeper. Pull the rebar out and measure the stain to get an indication of the depth of liquid concrete in the form. The length of the stain in feet multiplied by 150 pounds will give an indication of the concrete pressure in pounds per square foot at the location where the rebar meets resistance. This indicator, combined with other corroborating information, can help the pour manager determine whether the concrete is setting up as expected. Number 3. On some pours, it is difficult to know how the concrete is behaving in the form because the formwork design does not allow easy access to the recently placed concrete. As examples, large diagonal beams and columns may not allow a rebar probe down inside the form far enough to judge how the concrete is setting up. In these cases, alternative methods may be necessary. Another method is to monitor the behavior of concrete outside the form using a set of plastic buckets with lids. Use the buckets to sample concrete from each truckload before placing the concrete in the form. Mark each bucket with the time the sample was taken and the truck number. Monitor these concrete samples to get an indication of how long it is taking the concrete to set up. Do this with each load of concrete required for the pour, and keep track of how each concrete sample corresponds to a vertical height of concrete placed in the form. Understanding how the concrete is behaving outside the form will provide a useful indication of how it might be behaving inside the form. Number 4. Pour pressure monitoring sensors on form faces may be a good method for determining the pressure inside a form. Hollow core hydraulic jacks on form ties to monitor tie loads is another popular method to indicate pour pressure. Whichever method you choose, it is important to keep a pulse on how the concrete in the formwork is behaving. It is always a good idea to have a qualified member of the form assembly crew on hand throughout the pour to monitor the formwork and ensure that it is performing as expected at all times. Always keep in mind it may be necessary to change pour rates daily to compensate for changing concrete temperature and concrete additives. Inadvertently vibrating concrete in lower lifts may cause reactivating of the hardening concrete and increase pressure in the form. This could cause form failure. Additionally, excessive vibration of concrete may increase concrete pressure above liquid head pressure, and this too may cause form failure. Let's quickly recap our discussion. Every day we pour concrete, we need to determine the safe rate of placement to protect the crew and the project. Let's break it down into some simple steps. Step 1. Inspect the formwork setup to ensure that it is assembled according to the drawings with all ties, bolts, and nuts in place and tightened to specification. Step 2. Understand all additives used in the mix design. Find the chemistry coefficient and calculate the concrete rate of placement using a pour pressure chart based on estimated concrete temperature at time of delivery. Step 3. Carefully calculate the quantity of concrete required for the pour. Assign a knowledgeable member of the crew to manage the scheduled delivery of the concrete trucks and space out the delivery to approximately coincide with the placement rate as determined from the pour chart. Step 4. Understand and verify the behavior of the delivered concrete by pouring a sample into a bucket to monitor and confirm temperature. Step 5. Recalculate the pour rate based on the actual temperature of concrete. Step 6. Place concrete into the formwork at the assigned rate per hour so as not to exceed rated capacity. Step 7. Use an appropriate method of monitoring how the concrete is hardening inside the formwork. Step 8. Have an experienced member of the formwork assembly crew on hand to monitor the formwork throughout the pour. There is a need for new and improved concrete technology to meet the demand for taller buildings, longer bridges, bigger power plants, stadiums with more seating and parking, and more sophisticated water treatment plant facilities. Concrete is the preferred choice of designers, contractors, and project owners. And our responsibility as engineers and construction professionals is to rise to the challenges of the new technology by delivering quality projects on time for less than the estimated cost. And most importantly, with a safety record in which we can all be proud. Safety on the job site is everyone's job. Get the facts, look for potential form failure situations, and take vital steps to make sure the crew makes it home to their families each night.